Okay, so last time we developed dimensional analysis as a way of describing the equations of motion in physical systems. Namely, we work in some basis, and this basis can, for example, be given where dimensional quantities, mass, length, and time, say, defining basis vectors. We can express the other dimensional quantities as combinations of these ones. And we can construct, for example, an equation for some system in terms of a bunch of invariants. Invariants in the sense that they're dimensionless quantities. And if we have n parameters, and k vectors defining our basis, then the physical laws that describe our system can be described in terms of E equals n minus k dimensionless variables. And this is a content of the so-called Buckingham theorem that describes how to use dimensional analysis. Now, we then, in the tutorial, looked at Fermi problems, and in these Fermi problems, we're finding the appropriate dimensionless units to describe a system, and we express things in terms of a natural scale that appears. So, for example, there are a bunch of animal problems I took from Arnold's book on classical mechanics. And these animal problems is a natural scale, the size of the animal, and the size of the animal described how far it can run, for example. So the existence of a natural scale is used to describe the physics of various situations. Now, this is all good in the sense that we can get the units right, but the actual numbers that we associate to some phenomena we're describing, if they're in terms of this natural scale, that's generally going to give you the right answer, but not always. So you should be careful in applying dimensional analysis. So the last exercise on the tutorial was this Scharnhorst effect, where I claim the speed of light between Casimir plates is actually faster than the speed of light in a true vacuum. We can discuss the details of this effect, but the effect is basically a feature of the vacuum pair creating particles. So if you look at the natural parameters in the theory, if you want to compute delta C, the difference between the speed of light between the Casimir plates and the speed of light in an ordinary vacuum, this is something with dimensionful units. It's a velocity. And the other parameters, for example, the separation of the plates, the mass of the electron, and h bar. So if you construct something with units of delta C based on these quantities, you'll find that the natural dimensionless thing to construct is d mass of the electron delta C over h bar. So you can solve for delta C here, and delta C then would go like h bar d mass of the electron. This works out to be about 10 to the minus 3 meters per second, which is way off. If you want to consider the actual magnitude of the Scharnhorst effect for a separation of, say, a micron between these two infinite conducting plates, you'll find it's 1 part 10 to the 36 if you do a proper calculation. And adding dimensionless factors of 1 over 137, which we associate to QED, the coupling constant there, doesn't fix this. 1 over 137 can change this by a factor by 2 orders of magnitude, but that's not enough to explain the magnitude of this effect. So dimensional analysis gets you the right units, but it doesn't give you the right magnitude in this example. Another classic failure of dimensional analysis is in studying the vacuum energy density. So for our purposes, I'm going to work in natural units because I'm tired of keeping track of h bars and c's. So we'll set h bar equal to c equal to 1. And if we consider some scalar field theory, the scalar field theory will have an action that looks like this. So we've got some action for some scalar field phi. And the stress energy tensor, we compute in the usual way. So T mu nu is minus 2 over root minus g, variation of the action with respect to the inverse metric. And this works out to 1/2 du phi plus 1/2 g rho sigma d rho phi d sigma phi g nu minus d of phi g nu. And we want to consider when the energy in the scalar field is minimized. The energy is minimized when phi sits at the minimum of the potential via phi. So we have phi equals phi star, and v of phi star is the minimum. And when you're sitting at the minimum of the potential, you minimize the action, the energy, by turning the kinetic term off. So d mu phi equals 0. So you're just sitting at the minimum of the potential. Now, this tells us that in this case, the stress energy tensor, T mu nu, at the minimum, is minus v of phi star g mu nu, since these kinetic terms just drop out. So this is minus the vacuum energy density, g mu nu. And the equation of state here is such that the equation of state parameter is -1. So the pressure associated to this vacuum energy density is negative, and it's basically minus rho vac. So this action we describe is the action of an effective field theory. And we expect the effective field theory to be determined in part by Jejjala cutoff. Where do you trust the effective field theory? So if we want to estimate rho vac, the race was a bit too wet. We have some interval from 0 to mu, where mu is some Jejjala cutoff in our theory, and we're integrating dk 2 pi cubed 4 pi k squared times the energy we associate to an oscillator with this momentum, and this energy is 1/2 square root a squared plus m squared, where m is the mass we associate to this field. So the only natural scale in the problem where we expect new physics to take over is the Planck scale. So if mu is m Planck, then we worked out last time that in units where h bar equals c equals 1, m Planck is g Newton to the -1/2. And this works out to 10 to the 19 GeV. So we're essentially summing the zero nodes of harmonic oscillators all the way up to the Jejjala cutoff. When we do this, we find that this integral we can do. This integral is approximately u to the 4th over 16 pi squared. So square root k squared plus m squared scales roughly like k. So we're integrating k cubed dk. So if we plug in this value of mu into this interval, we'll find that rho vac is 10 10 to the 74 GeV to the 4th. Now, this is some quantity you can measure, or you can measure it quite well. For example, the observations of supernovae that describe the expansion of the universe. And when you measure this, you find the measured value. Well, we have the units, right? But the measured value is 10 to the minus 47. So we're off by 121 orders of magnitude. So this is a colossal failure of theory, in the sense that the natural expectation of our theory and the measured value are nothing near each other. So this is called the cosmological constant problem. Because this energy density is acting like a cosmological term in the Einstein-Hilbert action. This is in fact one of the two cosmological constant problems. A second cosmological constant problem is the energy density in the vacuum contributes to the total energy density at roughly the same order of magnitude as matter. And this is true only in a tiny epoch in the history of the universe. So we happen to be living in a period in the history of the universe where the energy density in the vacuum is roughly equal to the energy density in the matter. Why are we happening to live in this epoch? That's the second cosmological constant problem. Both of these problems have spawned a tremendous amount of research and papers and models to explain this. The thing is that no one believes their own model or the models of anyone else. So as a result, these problems remain open. As a result, we don't really know the resolution of these issues, but it's important we figure it out because this tiny vacuum energy density is responsible for driving the accelerating expansion of the universe. And we have no clue why it is what it is. So, we should be careful with dimensional analysis. So here, for example, we used to factor the natural scale of the problem in order to determine what a vacuum is. This is a standard thing we do, but it is leading us very far astray. So maybe we can do better. Maybe there's new physics that enters well below the scale. Maybe there's something supersymmetry, for example. Supersymmetry fixes this slightly, in that it's a 60 order of magnitude confusion rather than 120 order of magnitude confusion. But obviously it's not good enough. Yeah.
Is there any criteria to check if dimensionalities will fit other than comparing with non-results?
That's how you do it. You want to save yourself work. So use dimensional analysis to sort of guess the answer. If your guess is roughly correct, then you declare victory. And you may do a detailed calculation knowing that your guess is roughly correct. If your guess is totally wrong, you accept failure and you try to do better. There's no a priori way of knowing when these techniques fail. Yes?
So in the Shadow's force effect,
Yes.
how do you know that there is no minus sign or the delta sign?
You do a detailed calculation. Roughly speaking, what motivates this effect is the vacuum between the plates is different than the vacuum outside the plates. In between the plates, you have these are infinite conducting plates. You have electrons that have certain wavelengths between these plates. What slows light down is you send light traveling, and this light, for example, interacts with vacuum, with electrons that are pair created from vacuum. Because of these boundary conditions here, and because you can only fit certain wavelengths within the plates, there are fewer electrons that are pair created between the plates than there are in vacuum. Certain wavelengths are disallowed, or don't interfere with the propagation of photons between the plates. As a result, because there are fewer interactions, light is slowed down less, and light travels faster between the plates. So that's sort of the picture we have for what this effect is. You can do a detailed calculation and find the effect speeds up light by 1 part in 10 to the 36 between the plates. That's not something you figure out this way. And the only natural scales in the problem whether it's associated with electron mass, distance between the plates, and h bar to get something you can measure. The effect is tiny. It's much smaller than what you naively think.
So if we first require measured value here, then what is the scale of the mu? So order of
I don't know offhand, but one can easily compute this. Initially, people thought this was zero, and people thought there was some symmetry consideration that enforced the fact that it was zero. It was only the supernova measurements that indicated that there is a cosmological constant that's non-zero. The cosmological constant initially introduced as a flood factor in order to create a static universe rather than a universe that was expanding. It was only in 1925 that Hubble measured the expansion of the universe. So the Einstein static solution was unnecessary. It's also unstable, so it's a good thing it's unnecessary. The feeling then was there was no cosmological term, and it was only discovered observationally, and it was a surprise. The guys who discovered it won the Nobel Prize for noticing the acceleration and expansion of the universe. Okay. So we need to be careful. That's the bottom line. I want to now move on to using dimensional analysis in order to motivate renormalization group equations. So, renormalization group developed by Wilson in the early 70s allows us to organize physics in terms of scale. So I would say that in modern physics, modern being a little more than my lifetime, the two main revelations, the two main ideas that have revolutionized physics are the renormalization group and holography. Those are the new physical insights we've had into nature in roughly the past 50 years or so. The renormalization group and black hole thermodynamics developed roughly at the same time. And the renormalization group was pretty much understood once Wilson explained it to us, whereas black hole physics led in the early 90s to this idea that the gravitational systems in string theory of quantum gravity, the degrees of freedom of a gravitational system are secretly in one dimension less than you think. The degrees of freedom are codimension 1, and for example, in ADS-CFT, you can describe physics in anti-de spaces by conformal field theory, which lets on the boundary of the anti-de space. And the two notions are dual, and you can learn physics in the gravitational setting from studying non-gravitational physics because of this duality. So I would say these two are the main ideas in physics. And we've noticed that there was an entropy associated with black holes whose behavior we get mainly on dimensional grounds. So I want to argue that the second great advance in modern physics, the renormalization group, is also something we motivate on dimensional grounds. Okay, so my discussion here will follow a paper by Stevenson in 1981. And I'll put the full references up in my lecture notes when I post them on the school page. So I'm going to start by supposing that we consider some theory with a scale invariant Lagrangian. And the absence of a scale means that there are no dimensional couplings in the game. So there's no mass scales, there's nothing like that. Again, there are massive coupling constants in the scale invariant theory. So the task we want to set ourselves is to measure some observable rho of Q. Q is an energy scale. And we want to define, so rho is dimensionless, it's a function of some energy scale. And we want to determine the form of this function. Okay? So, for example, suppose you're working in a standard model. A dimensionless quantity you might want to compute is the ratio of the cross-section for electron-positron scattering to electron-positron becoming mu1, anti-mu1. So, this is something which is dimensionless, and it's observationally something which depends on the energy scale, and this is some quantity that we may want to compute in some theoretic standard model, for example. Okay. So, what do we know from dimensional analysis? What do we know from this Buckingham theorem that we discussed last time? So let's consider some function, say, f of x, y, where x and y are dimension flow parameters. So we know that if it depends on these massive variables, and f is dimensionless and uniquely defined, so f is dimensionless and uniquely defined. And we'll say, for simplicity, x and y both have the same units of mass. And the only thing this can be is f with the ratio of x over y. That's the only dimensionless quantity in the game. So Buckingham's theorem tells us we should expect a function like that. So as a corollary to this, if f of x and y is y independent, then it's also x independent. So in this case, if f of x and y is y independent, it's also x independent. And as a result, it's a constant. So here, where we only have one parameter in the game, rho of q has to be a constant. But we know that's not true. We measure this. We find that the difference in energy scale is such that r of q is in fact a function of the energy. Okay? So something went wrong in our application of Buckingham's theorem. What went wrong is the theory is not uniquely defined. So this assumption is an incorrect assumption. Why is it an incorrect assumption? It's an incorrect assumption because the get-out clause is that we have couplings in Lagrangian. We've got a one-parameter family of couplings in Lagrangian. It's not one theory we're looking at, it's a whole class of theories with different Baire couplings. So, Lagrangian is not one theory. It's a one-parameter family of theories. For many parameter family of theories with different Baire couplings. G0. So, because of this one-parameter ambiguity definition of the theory, we'll see that a scale enters through the back door. So I'm going to make a simplifying assumption here. I can dispense with a simplifying assumption by working iteratively, but it's more complicated to do that. So I'll just make the simplifying assumption, and you can look at Stevenson's paper, for example, to be a bit more general. So by simplifying assumption, it's going to suppose the theory specifies rho prime of Q. If the theory specifies the first derivative, then by dimensional analysis, the way things scale is d rho over q is equal to, or d rho dq, the first derivative, is equal to some function of rho, which is independent of the energy scale, divided by q. On dimensional grounds, there's nothing else it could be. So, this guy is dimensionless. And the choice of nomenclature here, beta of rho, is no accident. This will turn out to be a beta function. We can integrate this expression. And when we integrate this expression, we have integral dq over q is equal to integral d rho over beta of rho. So the integral of this is log of q plus a constant equals integral from minus infinity to rho, d rho tilde, beta of rho tilde, and this will be some function k of rho. Okay. So now we notice that k of rho is just a function of rho, and rho itself is dimensionless, so k is dimensionless. So the right-hand side here is dimensionless, whereas the left-hand side has log of q, where q is an energy scale. So because the units need to match, this constant I've introduced is going to be equal to k of rho of some scale mu minus log mu. And we can cancel the units here, and this is, if we introduce log of mu, we can do that. Okay, so this equation applies for any rho, for any scale mu. So the concept of integration here addresses this one parameter ambiguity in defining the theory. So this phenomena where some scale appears as an integration constant here goes under a name. This is developed by Coleman and Weinberg, and it's called dimensional transmutation. So looking at the expression we get from doing the integral, we can solve for rho, and we have rho of q is k inverse of k of rho of mu plus log q over mu. Okay. So this is assuming functions are nice and invertible and all that. So I'm not going to be mathematically rigorous. Let's just assume that the nice physical properties you want for functions are satisfied by the functions we're looking at. Okay, so equivalently, there's some scale. So this is for any mu. There's some lambda such that k of rho of lambda is equal to 0. If you're at that lambda, then we have rho of q is k inverse log Q over lambda. Okay, so this parameter lambda is dimension full, has units of energy, and just sort of appeared like a virgin birth. This is basically a consequence of this one parameter ambiguity we're talking about. We put this ambiguity in the unspecified nature of lambda, or equivalently, the fact this applies for any meter. Okay, so the theory is not capable of predicting what lambda is. That's what you need to measure. Okay, so everyone sort of happy with the story so far? Okay. Let's see what the next slide. So let's consider a particular theory. This theory will be G is SUNC QCD with NF flavors of quarks and NS Higgs bosons. So one of the classic calculations you do in your introductory quantum field theory course is to compute the one-loop beta function of the non-Euclidean theory, like QCD. So when you compute the one-loop beta function, you find, let's compute the one-loop beta function of alpha strong, which is G squared as a function of Q over 4 pi. So beta function, alpha S and Q, is d alpha S, d log Q. And this works out to be minus 11/3 C2 of G minus the number of scalars divided by 3, T, the representation the scalars belong in, minus 4 NF over 3 times representation of the fermions. And this is multiplied by alpha squared over 2 pi, which we'll call minus b alpha s squared. Okay, so that's the one-loop beta function of QCD. The Quadratic-Casimir, C2 of G, is so C2 of SUN is NC. And we define trace in some representation of generators TA and TB to be T of R delta AB. So you work out a similar representation for the scalars. You'll find that T of RS is 1. And if you work out the fundamental representation, the anti-fundamental representation for the quarks, you'll find that T of RF is equal to 1/2. And in the usual QCD story, there's only one Higgs boson in the game. So NS is equal to 1, NF is equal to 3, and C is equal to 3, and we have some beta function equation for QCD. The fact there's a minus sign here tells us that at strong coupling, at large energies, the coupling becomes small. So as a result, the theory is asymptotically free. And the discovery of this minus sign is what got Gross, Pulitzer, and Wilczek the Nobel Prize. I'll go talk about it first. He didn't publish. So if you have an important result, don't publish. Bad idea. So, using the technology we've developed, you can show that k of alpha s is the integral from minus infinity alpha s of b alpha s tilde over minus b alpha s tilde squared. And this works out to 1 over b alpha s. And using these expressions here, you can show that alpha s of q is alpha s of mu 1 plus b alpha s of mu log q over mu. This is true for any mu. And there exists some lambda such that alpha s q is 1 over b log q over lambda. And for QCD, experimentally, lambda at about 220 MeV, the coupling becomes order 1, and we're at strong coupling. Okay, so that's lambda QCD. So just knowing the beta function, we can develop these relations just using conventional analysis. Okay? Okay, so I want to now move on to deriving the RG equations. Okay, suppose we've got some observable, sigma, which is a function of momenta P1 to Pn. And these momenta all have units of mass. Okay? So, we know that we can write this expression by dimensional analysis as P1 to the d. So let's say the observable has mass dimension m to the d. You can write this as P1 to the d, sigma P1 over P, P2 over P1, Pn over P1. So that's what dimensional analysis tells us. There's nothing else it could be. Again, I'm assuming that P1 is not equal to 0, and these things make sense. Okay, but because there's one parameter ambiguity in the definition of the theory, we really should be looking at something which looks like P1 over mu, rho mu. Because there are these extra dimensionless parameters as a function of the energy scale, and the energy scale is mu here. Okay? So that's what the modification of dimensional analysis that led to dimensional transmutation tells us. This is the general form of sigma. So what we're going to do to analyze this is, well, I'm going to call this function f. I'm going to define a new function g. My new function g is equal to g of p2 over p1, dot, 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 pn over p1, p1 over mu, r. So r is just some function, and if r equals rho of mu, then g is equal to f. Okay. By construction. And g is independent of mu. If and only if r equals rho of mu. So, if g is independent of mu, then we have 0 is d by d mu, g, where we set r equal to rho of mu. we'll differentiate both the left-hand side and the right-hand side. So this guy is dg over d mu plus dg dr. So the definition here of, and then we have d rho d mu. And we're evaluating this at r equals rho of mu. So rho is a function of mu. So this guy here is just rho prime of mu. Okay? So let's multiply this equation by mu. We multiply the equation by mu, then we find that the following result holds. We have 0 equal to mu d by d mu, partials, plus u d rho d mu d dr of g r rho mu. We recognize this combination mu d rho d mu is logarithmic derivative. So this is the beta function. Okay. So we get the RG equation for an observable quantity, just purely on dimensional rings. Okay, so substituting sigma for g, we then have 0 is mu d by d mu plus beta of rho d by dr sigma. Right? So now as for observable quantities, there are also non-observable quantities that are relevant to understanding the quantum field theory. For example, a Green's function. So let's see what happens for these non-observable quantities as well. So before we do that, let's think about what happens when the beta function vanishes. The beta function of quantum field theory vanishes, we're at the conformal fixed point. So we'll hear more about conformal fixed points in the next lecture by Shinji. But when we have conformal field theory, we have scale invariance. So conformal theory enjoys scale invariance. So suppose we have a dilatation. Under a dilatation, x mu gets sent to lambda times x mu. So under such dilatation, an operator, O of x, gets sent to O prime of lambda x, which equals lambda to the minus delta O of x. So this delta is a scaling dimension. Of the operator O. Okay, so many quantum field theories don't live at fixed points. So things run with the energy scale. So for example, the couplings are not fixed. They're functions, the energy scale we're looking at. But on long, well, if you consider some interval in energy, things are roughly scale invariant. So in that situation, the scaling dimension of operators, delta, is delta classical plus gamma of g of the energy scale. So this gamma is called an anomalous dimension. And this will be relevant to considering non-observables and their behavior under the renormalization. Okay, so let's suppose we're considering some unobservable quantity. And again, it's going to be a function of the momenta in the energy scale. So some quantity is going to be a function of P1 through Pn, the scale mu. We express this behavior as mu to the gamma. Again, this is an observable quantity with dimension mass to the d. So P1 to the d minus gamma, phi of the ratios to be 2 over P1 dot Pn over P1, P1 over mu, rho over mu. Just as before. I'm going to use the same trick I used before. I'm going to define gamma as P2 over P1, Pn over P1, P1 over mu, and R. And gamma is equal to lowercase phi when R equals rho of mu. So the way I've organized phi, all the energy dependence is in front, and this little phi is a dimensionless quantity. Okay? So mu and P1 carry this mass dependence. Okay, so let's take a derivative. Taking a derivative, we find that d phi, d mu, keeping the pi's fixed, is equal to d gamma, d mu, keeping pi and r fixed, plus d gamma, dr, keeping pi and mu fixed, rho times mu. So from this equation here, we know what the left-hand side is going to be. The left-hand side is going to be gamma over mu times phi. Okay, just taking derivative here. So if we multiply by mu, we get 0 is mu d by d mu plus beta of rho d by dr. So this is the same term as we saw previously. There's going to be another term associated to this gamma. So minus gamma of gamma. And we evaluate at r equals rho. Okay. So this is a renormalization group equation with the anomalous convention in place, as it should be. Okay, so we get the renormalization group equation. And the behavior renormalization group equation with respect to mu is fairly simple. And it has to be fairly simple because when we construct observable quantities out of these unobservable ones, for example, by computing some amplitude, something which is physically observable, all this dependence on the gamma has to drop out. Okay, so gamma is independent of PIs in order to keep this simple. Otherwise, these miraculous cancellations can never happen. Gamma, however, is a function of the energy scale. So gamma is gamma of rho of mu. So there is dependence on the scale. But in calculating the physical observables, these dependencies need to cancel. I guess I'm almost out of time. So I just want to say in this lecture, we've motivated the renormalization group structure just by looking at how things behave dimensionally. So the power of dimensional analysis is such that when you're studying quantum field theories, a lot of the structure of the quantum field theories is just evident on dimensional grounds. There's nothing else it could possibly be, and it works exactly as you expect it would work. So the idea of the renormalization group again is we're allowed to organize physics according to energy scale. And for example, where I said our effective field theory is valid up to the Planck scale in analyzing the cosmological constant at the very beginning, what I did was I said there's a new scale which physics enters, and at that new scale, below that scale, we generated out physics in the ultraviolet, and as a result, we have some effective theory of physics at low energies that works pretty damn well. The way we do physics basically is we think like Wilsonians. There is no such thing as well, there are wrong theories, but theories that are replaced by better theories are often replaced with better theories not because they're wrong, because you're outside the original validity of that theory. So this explains why four Fermi theory is a good description of how four fermions interact at some energy scale. But if you want a more detailed description, you go to a scale where there's some intermediate vector boson. So we were able to organize these theories at different scales based on the renormalization group structure. The renormalization group structure is evident just from looking at how things scale. Okay. So I guess that's all I want to say, so thank you. I guess we'll take a 10-minute break and then we'll resume the show.